Welcome to a lesson with Dr. Powell. Let's talk about how we can take a linear transformation that's written with respect to standard coordinates and write it with respect to some skewed coordinates. So this right here makes up, so A will look something like this going down, and B looks like something like this going up. And if we were to make a coordinate system relative to this, and take our coordinates with respect to AB coordinates, we want to know what this linear transformation looks like with respect to those coordinates. If all of our vectors were written with respect to these, like 2, 3 AB, for instance, would look like you follow A twice, and then you follow B 3 times, and it would be right there. So we kind of like this, the vector from here to here would be 2, 3 and AB coordinates. Okay, so we want to look at this linear transformation with respect to those coordinates. Is there a matrix that can describe that? And how do we come up with that? All right. So what we do is we build what we call the unpretending matrix. All right. So it's kind of like we're going to make a matrix that pretends that A is like E1 and B is like E2, that does this linear transformation right here. But first, what we're going to do is we're going to assume that we're already in AB coordinates. So we have some vector in AB coordinates, and we're going to multiply by something that unpretends. That puts it back into standard coordinates. Then we'll run the matrix A, and then we'll run another matrix which pretends us back. Thinking of function composition. Under a column interpretation, so multiplication is done, it follows the same order as the composition. Okay, so that's kind of what we're looking at. So what's the unpretending matrix? It's actually pretty clear. We just look at these vectors right here, 1, -1, 1, 2. That's the unpretending matrix. All right, so because think about it, when you put E1 into here, it unpretends it. Put E2 into here, it unpretends it. Okay, so that's our unpretending matrix. Next, after we run A, we need to pretend again. Now, what's the pretending matrix? It's the inverse of the unpretending matrix, so we just got to find the inverse of this guy and put it right there, and we'll call it the pretending matrix. You could write this as, if you want, you could write this as U inverse A, or you could write it as P inverse. It doesn't quite matter which way you want to write it, but it means the same thing, and it produces the same result. So that linear transformation in AB coordinates. Okay, so let's find out what this pretending matrix is. We simply take the inverse of this guy, and we can let's just do row operations. So we have 1, 1, -1, 2. Row operations, it takes us to the identity matrix. So first, let's airdrop with the 1. So 1 times this row plus that row, and that would give us 1, 1, 0, 3. Okay. And then what we could do is we could rescale this row by a third. And so we end up getting 1, 1, 0, 1, and then we airdrop up, multiplying this guy by -1 and going upward to get us 1, 0, 0, 1. So we follow these exact same steps on an identity matrix, and that'll give us the inverse. So let's see what's being done. The first thing was to multiply by 1 and add down, so that's a 1, and then rescale this guy by a third. Then the last thing is just -1 times that and add it up. So that would be a -1/3, and this would become a 2/3. And there we have it. So we have 2/3, -1/3, 1/3, and a third. Multiply this out, we will, so these guys right here, will get the desired matrix. So we can do so. All right, and multiplying them out. Let's see, easiest way. Well, let's multiply these two together, I guess, first. So if I did a row interpretation, this row would pick out that right there, 0 times that, 1 times that. So the top row of AU would simply be -1, 2. And this guy picks out -1 times the top row, so -1, -1. So that's AU multiplied together. Now I need to multiply it to that guy. 2/3, -1 third, 1 third, 1 third. Now to make this simpler, maybe I'll just factor out 1 third out of that matrix. Okay, so I can look at it more simply. So that's what 2, -1, 1, 1, with 1 third out, and -1, 2, -1, -1. Now I matrix multiply these two guys and multiply by 1 third afterwards. So in doing so, let's think. I'm going to do a row interpretation. So I'm going to say that. So 2 times that row plus -1 times that row. So it's basically just adding 1, 1 to whatever we get when we double that. So -2, 4, but you add 1, it should be -1, 5. So we end up getting -1, 5 on the top. And then the bottom, you just add these two rows together. So you get -2 and 1. And then that's 1 third. So this should work as our matrix. Okay, so let's actually check this out for a minute and see if this is working properly, at least just in one instance. Maybe a simple one to check would be to think about let's think about E2 and what E2 looks like in AB coordinates. So that's an interesting question. Let's just erase this here and just think about that for a second. So E2 in AB coordinates, actually, we have it right before our eyes. The pretending matrix tells us how to pretend with E2. E2 pretends as this. It's basically a -1 third times 1 third times the vector -1, 1. You see that? That's -1, 1 times 1 third, or -1 third. 1 third, just factor the third out of that vector right there. That's the image of E2 when we pretend. So this is the vector right here, that E2 is an AB coordinate. So let's actually apply this transformation on E2 when it's in AB coordinates and compare that to what actually happens when we apply this transformation to E2 itself, written as E2 in standard coordinates. All right, so how do we do that? Well, simply what we're going to do is we're going to take this guy right here and input it into this matrix function here. So we can think -1, 1, and you're multiplying by 1 third. Just remember that, just 1 third off the side here. So what does this mean? This means -1 times that column plus 1 times that column. Basically, you're just saying 1 plus 5, 2 plus 1. So it's 6, 3. So 6, 3 multiplied by 1 third would give us 2, 1. So we're looking at 2, 1, but then you multiply by that third. So 2 thirds, 1 third. Okay, is the result. All right, is the result. Now notice that 2 thirds, 1 third happens to be exactly what E1 pretends to be. And that's exactly what we want, because notice that this linear transformation, it takes E2, and where does it take it? It takes it right to E1. Whew, well, and this takes E2AB, and it outputs E1AB, which is exactly what we would like to see. So it looks like what we found right here is the right matrix, and it's doing the right job right here. Thanks for watching.